is that the empty set and the set omega are measurable sets, okay? And why is that? Okay, so I call them A measurable. And I call them A measurable because, and the reason for that is, of course, because both the empty set and omega are elements of the sigma algebra. You remember that. So if the empty set is not in there, then it cannot be a sigma algebra, okay, because it cannot be closed under complementation. And if omega is not in there, then it cannot be closed under countable units either. So that's basically one statement, which is quite easy, okay, because if that was not the case, then, all right, so these are measurable. Of course, the image of the empty set is 0, so then the empty set is a measurable set, okay? All right, so I use the expression A measurable, all right? So measurable with respect to the sigma algebra, so that means that the measure is defined on that sigma algebra, all right? Good, that's the first statement. So second statement is that if, let's say, a set A is measurable, okay, so I call it A measurable, so that means that actually A is an element of the sigma algebra, capital A, right? Then the complement of the set A is also measurable. Okay? So I call it rather A measurable, okay? Okay? Why is that? Okay, so that means that the statement here is true. So that because actually the sigma algebra is closed under complementation. So if something is in there, then its complement must be also in there. All right? Okay? Got the point? Because otherwise it would not be sigma algebra if it is not closed under complementation. Okay? So if a set, okay, so if this set is measurable, then its complement must be also measurable as well. Okay? And of course, a countable union and countable intersections of measurable sets must be also measurable. Okay, so due to the sigma-additivity, that is true by definition. But since it's also actually measurable with respect to the complementation, that is also true for countable intersections. So a countable union, okay, the countable union and countable intersection of measurable sets okay, is also measurable. Okay, so or let's say rather A measurable. Okay, so I call it A measurable. Okay, that's actually better. Of A measurable sets is also, or are, sorry, okay, are also A measurable. So actually we showed this, okay? So this means that, okay, so if certain sets A1, A2, etc., are all elements of the sigma algebra, then this implies that the countable union, okay, so their countable union must be also an element of the sigma algebra and a countable intersection as well. Okay? So this is just the same statement formally, okay? How can we go back? So the countable union and countable intersection of A measurable sets are also measurable, okay? So both, okay? So both are elements of the sigma algebra. This is actually something that I already showed, okay? But I would like to repeat this here, this statement, okay? So if these countable sets are all elements of the sigma algebra, then the countable union will be also an element of the sigma algebra and the countable intersection as well, okay? The countable intersection follows actually directly from the laws of De Morgan, okay? So we have that, okay? Now, guys, there are also some, I mean, this is elementary, actually, because that is something we also already considered, okay? So I'm just repeating it myself, okay? These are the properties of sigma-algebra, and just what I add here is the expression measurability, okay? So measurability actually means, to put it simple, that it's an element of the sigma-algebra on which the measure is defined. Okay? Now, other properties of a measurable function include the following, okay? And I'm going to put this as a lemma right now. So the first property includes the monotonicity, okay? So first off we have the monotonicity, okay? So this means that if you have, let's say A is a subset of B, okay? And B is a superset of A, right? And this implies that the image of A cannot be larger than the image of B, okay? So the image of A cannot be greater than the image of B if, let's say, A is a superset of B, okay? Because actually, in general, B has more elements in it, okay? So let's say if you have, let's say, for instance, a length function, okay? So if two people, I mean, let's say if one person is not taller than the other, okay, and that means actually that the measure of the height of the person cannot be greater than the height of the other. Okay, so that's actually simple. All right, and this property is called the monotonicity property. Okay. So if A is actually a subset of B, which means that in general case B has more elements in general than A. Okay, then let's say the length of the set A cannot be greater than the length of the set B. Okay, so this is quite intuitive. Okay. That is also true for probability, guys. Remember from probability theory, right? So if, let's say, A is a subset of B and A is an event, and okay, here so A and B are events, and the probability of A cannot be greater than the probability of B. Okay? All right? For instance, the probability, I mean, if you, let's say, the experiment is that you pick out a random real number, okay? So the probability that you pick up a positive number cannot be greater than the probability that you pick up, let's say, a real number, okay? So that makes sense. Okay. Now this is the monotonicity property. Okay. Now you have also the so-called subtractivity. Okay. So this is called subtractivity, and subtractivity means that here we have, and this is if, let's say, A is a subset of B, and the image of A is finite, then what you have is that the image of the difference of B and A is equal to the image of B minus the image of A. Okay? That is also quite elementary, and you also know this from probability theory as well. Okay? Now the third property is that the so-called inclusion-exclusion principle. Okay. Inclusion-exclusion principle. This states actually that the measure of a union, okay, it does not have to be a disjoint union. So this is an arbitrary union, so measure of the union of two sets. Remember, these two sets do not have to be automatically disjoint, is equal to the image of, or the measure of A plus the measure of B minus the measure of the intersection of A and B. Okay, so this is what the so-called inclusion-exclusion principle is about. Okay. Okay. So maybe you can, I mean, let me just demonstrate that. So here, for instance, you have the set omega. Here you have the set A, and here you set B. Okay. And this will be, let's say, the area of the union. Okay, the area function can be also a measure. Okay, so the area of the union is equal to the area of A. Okay, so let me just demonstrate that. So this will be the actually equal to. Okay, so now here the area of A. Okay, so we have the set A here. This will be the area of the set A. No, sorry. Alright, so the area of this set. Okay. Then plus the area of the set B. Okay. And you can see that clearly that you have the area of the intersection twice in there, right? So then you subtract actually the area of the intersection of the two, okay? So this is the intersection here, guys, okay? Okay, so you get the area of A plus the area of B minus the area of the intersection, then you get the area of the union. That's it. And this is the inclusion-exclusion principle, and this directly follows from the definition of measures, okay? So that's how we define them. Okay? Understand this? Okay? Now, and there is also the so-called, and this is the next property here, so this is the fourth, all right? And the fourth property is called sigma-subadditivity. Okay, so subadditivity, okay? That's the next property here. So, and you can clearly see this actually from the exclusion-inclusion principle. So this means that the image of a countable union, okay, countable sets cannot be greater than the sum of the images. Okay. And we have that for, this is true for any A1, A2, etc., which are element of the sigma-algebra. Okay? So these sets, of which actually the union consists of, do not have to be pairwise additional. Yes?
Why does this sum only go to n?
So to the plus infinity, yeah. That's correct, because I was stupid. That's the reason. Okay? That happens sometimes, still. Thanks. Okay? All right.
Excuse me.
Yes?
Do AI have to be pairwise?
No, they don't. That's why. Okay, so this is just an arbitrary sum, just like here. Okay, this directly actually follows from the inclusion-exclusion principle. Okay, somehow, because you can see this here. Okay, so in general case, I mean, you can see this here. Maybe you see this, that this implies actually that, I mean, let me just add this here so that the image of the union of the two sets is not larger than the sum of the images, right? Okay? So it's either equal or greater. The sum is either equal to the image of the union or greater than the image of the union. You can see this here, okay? So if the image of this is actually 0, right? So if the image of the intersection is 0, then we have that the image of the union is less than the sum of the images, right? Okay? You see? So that follows from the exclusion principle, let's say, for finite unions. Okay? But since the function is sigma additive, that also implies that the function will be also sigma subadditive. Okay? Which means that the image of a union, no matter if the sets are pairwise disjoint or not, is not greater than the sum of the image of the sets of which the union consists of. Okay? And this is true also for countable unions, not just for finite unions. Okay. Good. All right. Now these are properties that we also consider. And there are two properties which are very important again, so I will put this in theory. I'm not going to prove this here because due to lack of time, what I will actually demonstrate what it is about. So first we take it as it is, okay? Just my mother-in-law, I have to take her as she is, okay? So we take that as it is first, and then we try to understand what it is about, okay? After that, I also try to understand different things. Sometimes it's very hard for me to explain other people, okay? Let me just make the statement here, but anyway. I cannot believe I'm recording this. I don't know what is listening. Okay, so this will be a theorem. Okay, so suppose that this, suppose that we have a measure. Okay, so we have a measurable space. So this will omega, the sigma algebra and mu denote a measurable space. Okay. Or measure space, sorry. I mixed it up. This is a measure space. And then the following property holds. Okay? The first property is called sigma continuity from below. Okay? That's why I started. So this is called sigma continuity from below. Okay? Okay, so what does that mean? Okay? This is actually a property that also there follows, but this is very important. Now this means that suppose that you have a sequence, that a sequence of sets, so these are all, let's say, measurable sets, okay, and they have also the property that set A1 is a subset of set A2, which is a subset of A3, and so forth, okay? So we have an increasing, let's say, an increasing sequence of sets, okay? The first one is a subset of the second one, the second one is a subset of the third one is a subset of the, you know, and I will give you an example so you can see that then. So then, what you have is that the limit, okay, so the limit of the image, the last one, okay, so the limit of the image of the last one, okay, will be equal to the image of the union of these sets, okay? This is what sigma continuity from below means, okay? I will come back to it. It sounds a little bit complicated, but let me just make the statement here. So the limit of the image, okay, will be equal to the image of the union, all right? You're going to see this, all right? Good. That's actually the first statement that I would like to make here. All right. So you see that. The second statement that is also true, and you're going to see this, okay, will be about the sigma continuity from above. Okay. So that's the second property. This is called sigma continuity from above. Okay. And you have, what you have here is the other way around. So suppose, okay, suppose that here, these sets, this is actually a decreasing sequence of sets, okay? So A1 is a superset of A2, A2 is a superset of A3, A3 is a superset of etc., etc. And then what you get is that the limit of the image, all right, so you have actually the last one and then you take the limit of them. Okay, so the limit of the image will be equal to the image of the intersection of the two, of the intersection of these sets, okay, in that case. I will give you an example, so hopefully you understand this, okay? Now, okay, so this is what the statement is about. So, okay, very hard to understand formally, let's say, okay, but I will give you an example so maybe I can demonstrate that how it works, okay? These two things, so sigma continuity from below and sigma continuity from above. All right. Now, let me just consider the following example. So, hopefully you see this. Do you have that? Did you copy this? Okay. So then, hopefully you understand what it's going to be. Okay. So, for instance, let's just consider an example, and I will define a measure that satisfies this property. Okay. So, suppose we have, for instance, an, and an will be some kind of these open integrals that I really actually considered here. So this will be, and I will define as follows. Okay, so we have the interval from the lower bound of the interval to be -1 plus 1 over n. And the upper bound will be 1 minus 1 over n. Okay? And I'm going to define a measure. Okay, so the measure, so for an interval from a to b, okay? And this function will be a measure, okay? So I'm not going to show this, but you can see that here. And this is defined as b minus a. Okay? So b minus a will be actually the length of the closed interval. Okay? You understand? Now, the question here is, what will be the length of an open interval? Okay, so this is the question that I will answer. And this property, namely the sigma continuity from below, this will help me to answer that. Okay, so here, this is the basic question that I asked. What would be actually the length of an open interval? Okay? All right? Now I'm using that property. Okay, so maybe you can actually, we can check it out how it works. Okay, so suppose we have n here. Okay? Suppose we have the interval, I mean, we look at the interval itself. Okay, so how does it look like? And we also look at the, actually, of the length of these intervals. Okay, so what is going to be, so what's going to be the image of the corresponding interval? Okay, so the length of the closed interval. Now, okay, so let's start with n is equal to 1. If n is equal to 1, then you have -1 plus 1 over n equals 0. Okay, so 0, and 1 minus 1 over 1 equals also 0. So you have the closed interval that has 0 as its element. Okay, and the length of that will be 0, of course. Right? So the interval from 0 to 0 actually has a length of 0. So that will be the image of that. All right? As you can see, just because the image is 0, it doesn't mean it has to be empty. Okay, so this interval is not empty, guys. It has at least one element. Okay? Now, if n is equal to 2, then what? Then you have here -1 plus 1 over n equals -1 over n, 1 over 2, sorry. And here 1 minus 1 over 2 equals 1 over 2. So this is actually the interval from -1/2 to a +1/2. And the length of that would be equal to 1/2 minus 1/2 equals 1. So this is the length of the interval. Understand? Okay? Now this is actually how it goes. Okay? So, and for 3, we can also do that for 3. Okay, so we have -1 minus 1 over 3 equals -2/3. And 1 minus 1 over 3 equals +2/3. So the length of that interval equals 4/3, right? That's obvious. So 2 over 3 minus -1 or 2 over 3 equals 4 over 3, right? Just 4/3. Good. Now we could continue, guys, but you can see this here. So what we have here is actually that this is a subset of the second one. So the first one is a subset of the second one, right? You see that? Okay. And the second one is a subset of the third one, right? Okay. You see? Okay. And the fourth one would be also a subset of the third one. Okay, so that goes on and on and on. Okay, so basically it's quite clear, right? Now, due to that property that we have here, because that's what you're trying to figure out. So what would be actually the limit of the image, and this is what you're going to look at. Okay, so and this is what you see here. So what's going to be the union of these intervals? Oh, sorry. Okay, so what is going to be, or the image of the union, let's say, the union of these intervals. You can see this here, so this is going to be 1 minus 1 over n. Okay, so the union of these intervals will be equal to the open interval from -1 to 1. Okay, so that's actually what we get out of it. All right. So we find out actually what this interval is going to be like. Okay? Now, And let me just phrase that. So how would you actually compute this? Okay, so you would actually the length of this interval here. Okay, so the length of an open interval will be equal to the length of this total union. You see? Okay, so this will be the length of the countable union. Okay, so and it goes from 1 till plus infinity of these intervals. Okay, so you have negative 1 plus 1 over n for the lower bound, and you have 1 minus 1 over n for the upper bound. Okay, that's quite obvious because if these two sets are equal, then the images must be also equal, right? Now, due to the sigma-additivity property, this will be equal to what? And you can see this here. This will be equal to, and this is where the sigma-additivity, sigma continuity from below here first appears. And so due to the sigma continuity from below, we have that this will be equal to the limit of what? This will be equal to the limit of the image, actually, all right, of what? And then the last interval, okay, so from negative 1 plus 1 over n, so 1 minus 1 over n. So here, and that will converge to plus infinity, okay? You understand? Okay, so this will be actually equal to the limit of this image here, okay? And this is equality directly follows from this property, so sigma continuity from below, okay? So these two things are equal due to the sigma continuity from below. And what's the length of that interval here? You can see this here. So what's the length of that interval? So the upper bound minus the lower bound is equal to what? Okay, so this is the limit of, and you can calculate this here due to the definition. You can see that so the length is defined for closed interval. So this is b minus a. So this is the upper bound minus the lower bound of the closed interval. Okay, so let me just put it here. So 1 minus 1 over n minus negative 1 plus 1 over n. Okay? You see? All right? So then this, as n approaches infinity, all right? So what's going to be? So this will be 1 minus, you can see this here, 1 minus 1 equals 2, all right? And negative 1 over n minus negative 1 over n equals negative 2 over n. You see? So as n approaches infinity. Okay? So, and this is equal to, I mean, of course, as n approaches infinity, you get the limit that this is going to be equal to 2. Okay? And that is a property that all measures must have. Okay? So if a function is sigma additive and the image of the empty set is equal to 0, then it's also satisfying this property, namely the sigma continuity from below. Which means that, as a consequence, you get, okay, so here we, as just actually to sum it up, so the length of this closed interval here, okay, so between negative 1 and 1, okay, which is obviously equal to 2, is going to be the same as the length of the open interval. Okay, so this property enables us, okay, to assign actually, I mean for open intervals, to assign actually the length, okay, even though the function is defined for closed intervals. You understand this? Okay? So if you have, let's say, an interval, a closed interval from 0 to 1, and you take out the upper and the lower bound, okay, the length of the interval doesn't change. See? Just because you take out the upper and the lower bound. Okay? You understand that? And this is due to the sigma continuity from below property, namely that all measures have to satisfy. Okay? That's also weird. Okay? All right? I mean, of course, you get what you get is actually not is actually a subset. So this is actually a subset of that one, but the length of these two are equal. Okay? Because the length of a single point, guys, is equal to 0. That's the reason. All right? Just as the area of a straight line is also equal to 0. That would be also another consequence. Okay? Now this doesn't actually prove that the sigma continuity property from below is true, but you can see this clearly that how it works, okay, from this example. So how I can use this property to calculate the length of an open interval if I tell you what the length of a closed interval would be like. Okay? You want to ask something?
Yeah, I just wanted to ask if it's okay to not find this very intuitive, just like learn it.
Yeah, I'm just using it here. So basically, did you find the example not intuitive, or did you find the statement not intuitive?
The statement.
Okay, so the statement itself, there is a proof of that. The proof is in the lecture notes. Okay? So what I can do here is I can explain what the property means. Okay, so the limit of the image, let's say, must be equal to the image of the union of these countable sets if, let's say, that you have a sequence of increasing sets, which means that the first set is a subset of the second one, the second is a subset of the third one, and so forth. Okay, and that property just helps us to assign actually the length of open intervals if the length of closed intervals is defined. Okay, that's the only thing. Okay, and the same thing for the sigma continuity from above, which could also, if the length of open intervals is defined, then we can assign length for closed intervals, so that would be the other way around. So if you know what the length of an open interval is, then you already know what the length of a closed interval will be. And if you know what the length of a closed interval would look like, then you automatically can define what the length of an open interval would look like. That's actually what the implication of this property is. Okay? So for instance, for a continuous random variable, the probability that x, for instance, a continuous random variable, is between a and b, which will be just as large as the probability. Maybe you know this for continuous random variables, right? So there's an application that maybe you see. So let's say x is continuous. Okay, so normally distributed maybe. So this is something that you know. So the probability that, let's say, x is between, let's say, a and b, where actually x can be a and b as well, will be just as large as the probability that x is strictly between a and b. Okay? Maybe you know that. Remember that from probability theory. That is also true for the normal distribution, maybe. Okay? Okay? And that is an implication on, which is based on this property that we're talking about, namely the sigma continuity from below and the sigma continuity from above property that we actually were looking at. Okay? Good. Now that is an application. I want to stop here, and I will continue next Wednesday. We're going to be defining what the probability measure will be. Okay? So if x is continuous, then this is true. And that is an application. Okay, but that's the reason for that. Okay? Good.